So, radiative balance. What we're going to talk about is describing the evidence for Earth's radiative balance. So, what the Earth can prove and show that it has heat sources and heat coming in, and it's also re releasing it back out into the atmosphere. You're going to know what insulation is again. We've talked about it in previous presentations, and radiative balance. And we're going to be able to describe 4 ways the atmosphere is heated. So, it's a condition in which a body gives off as much heat as it receives. So, however much heat comes into it and is put into it, it's going to re release that same amount. So, it's going to have an equal out to being balanced. The insulation from the sun is going to equal the infrared energy from the earth. So, you'll see that you have ultraviolet rays coming in. They're going to heat up the earth, and that's going to be re released as long wave infrared. Short wave UV, long wave infrared. Whatever comes in is going to come back out. That's that radiative balance. So, the evidence for this you can actually see daily. So, you'll notice that the sun comes up at 6 a.m. and it's actually at the coldest temperature. We'll talk about that in a second. But when the sun comes up and it's going to get increasingly up higher in the sky, and at noon, the maximum temperature does not happen until a couple hours after that. Why the lag? That's what it asks here. Why does it take so long? Well, it's because the sun needs to be out for a long period of time, and it takes time for things to heat up. It takes time for land to heat up. It takes a longer time for water to heat up. So that's why the warmest time of the day is not when the sun is at the highest point, but when the sun has been out for the longest period of time. Same thing happens in the morning when the sun has been down for such a long period of time. It takes time for all that heat energy to be re released into the atmosphere. So, right before when the sun comes up and right when the sun comes up, that's going to be one of the coldest times of the day. Okay. So, you can see this also through the course of the year. So, we know that the coldest time of the year is going to be our minimum temperature. It's going to be the end of January, beginning of February. Why? Because the sun has been at the lowest angle in the sky all the way up until that minimum temperature. So our shortest day of the year, sun's at the lowest possible angle, should be the coldest day of the year, right? Not so much. What happens is because it's been at that low point, it's had some time between November, December, and the beginning of January to cool everything down, that our coldest temperatures don't happen until the end of January, beginning of February. Then when we know March hits, it kind of starts to reverse. Okay. And then the sun's been out, it's getting higher up in the sky. It's going to be out for longer periods of time. So that means that that maximum insolation, the highest point in the sky, is not when it's the warmest. It's going to be the warmest a little while afterwards. So that's why at the end of July, beginning of August, our maximum temperature here in New York State is going to be the warmest after that sun's been out and warmed things up for a longer period of time. Again, same thing happens on the daily schedule. This is just over the course of 24 hours, which we already talked about. Okay, those you are going to need to know how to use for your worksheet. So if you need to rewatch this or you need to look at it and kind of break it down yourself, that would be a good idea. Now, evidence of radiative balance, the hottest and coolest times of the day. So the warmest is going to be between 3 and 5, usually at about 4 o'clock. And the coldest is going to be around 6 o'clock. It is not at, well, 4 p.m. today, Miss Baker said it's going to be the hottest it is. No, it's around that time is when it gets to be the warmest part of the day. That's normal circumstances. If you have a cold front coming in, that's going to throw it off a little bit. So it's not always true, but that's what the majority of the time, this is what happens. Okay. And then the hottest and coolest times of the year, usually the hottest time of the year is going to be between July and August. Coldest is between January and February. Remember, hottest time of the year, the sun's been out for a longer period of time. It's had time to have that energy build up to create all that heat, and it's going to be the warmest days of the year. January, February is the opposite. The sun has been lower in the sky, it's not out for as long, and it's going to cool things down enough that we're going to have those colder temperatures. Now, is Earth really in a radiative balance? Yes. Whatever comes in, the Earth wants to re-radiate back out. Does it always balance itself out? Well, there's some factors that get in the way. So over long periods of time, it does look like this. During short periods, though, it kind of varies from year to year. So it depends on different circumstances, like if there was a volcanic eruption or if there was heat being released from the ocean through an El Nino, if there's all these different factors that can change things. But on the big picture and the scales, you can see that Earth does try to balance itself out. So, heating the atmosphere, you have direct absorption from the sun, re-radiation from the earth, you have conduction, and then you have latent heat of condensation. So, direct absorption, sun has UV rays, it comes in, earth absorbs it and re-releases it in long wave, and it's transferred into heat energy. Re-radiation of long wave and radiation from Earth's surface. So this is when the shortwave radiation is absorbed by the Earth. So the UV rays come in, actually heat up the Earth itself. It's re-radiated back through infrared radiation. This is also called terrestrial radiation. Terrestrial meaning like solid rock, like our terrestrial planets. And gases in the atmosphere absorb this infrared re-radiation and are heated. So the infrared waves that are coming from the earth are actually heating the air around it. That's what's creating more heat. So not only do the UV rays coming in heat the air, but also the infrared rays coming up that was heated by the sun as well, that's also heating the atmosphere as well. So this picture, you can see you've got UV rays coming in. You can heat things up, like you can heat up ice, you can heat up the water, you can heat up the land, you can heat up the ice sheets, and it's going to re-radiate back out. Some of these things don't heat up as much as others, like land will heat up way more than the sea ice or the ice sheets. So that's going to put off more heat energy. The water will also bring off more heat energy. Water takes time to heat up and cool down, though. That's key. So, conduction. This is the transfer of heat energy by direct molecular contact. So that means that one rock touching another rock can actually transfer heat that way. And sometimes the hot rocks themselves are contact with the atmosphere. So that's what's also heating them up. If you've ever been outside and you've walked on the black pavement with your bare feet, you burn your little tootsies off, right? That's because you're using conduction, that heat transfer from the blacktop to your foot, and that's what's heating it up. And that's also what you feel coming off of the rocks as well. Latent heat, this one's a little bit different. We're going to talk about this more so when we get into more of the meteorology part of our units, not just the Earth's atmosphere. Well, what happens is that water vapor condenses to liquid water. When it condenses, it releases the heat energy that it had, and this can create, or it has this latent heat effect. So what happens too is when water evaporates, it's taking heat energy and it's going to cause a cooling effect. So for example, when you get really, really hot, your body needs to sweat. And when it sweats, you have water all over you. When the water evaporates, it needs heat energy in order to evaporate. So it's taking the heat energy away from you, and it's going to cool you down, and it's going to put the water vapor up into the atmosphere and pull it away from you. So your body has a natural system of taking that water, it then evaporates and it cools you down. If you don't sweat, you don't cool down as fast. Okay, same thing when it condenses, though, it's going to release that heat energy. But we'll talk about that in our other slides when we get towards meteorology. But yeah, isn't that weird that your body sweat may help form a cloud? So just think about it. When you are outside catching raindrops in your mouth, you could be catching sweat from somebody else. Ugh, ugh. The heat budget. This is the result of balance between the total amount of energy it receives from the sun and the total energy it gives off. So the heat budget is whatever comes in, the same amount is going to go back out. Same thing in radiative balance. So, what causes the heat budgets to shift? What causes these heat budgets to, with whatever comes in, the same amount doesn't go back out, or too much goes back out, or for our case, mostly it's how much doesn't go back out, how much gets stuck in our atmosphere. So, we have changes in solar energy, changes in Earth's orbit and axis and tilt, volcanic eruptions of climate change, human causes. There's a couple human causes we're going to talk about. Solar energy. There's these things called sunspots, and they cycle every 11 years. It's a darker region of the sun's visible surface, and it causes, or higher numbers of sunspots emit more energy. So they're going to cause a heating or cooling effect depending on what's happening. And as you can see from this chart, they're happening every 11 years. However, in like around the 1960s, there was a big sunspot uprising. Okay. Changes in Earth's orbit and axis and tilt. Earth's axis will tilt ever so slightly different. So if that happens, and it happens over thousands of years, it's kind of changed how our seasons are and how drastic our winters or summers could be. So if the tilt changes a few degrees, our eccentricity can change a minor amount. And when this happens, summers can be cooler, winters are warmer. You also have more precipitation. You could also have more storms. This is what happened during the Pleistocene Ice Age. Volcanic eruptions. This one could be scary because if if that ever went kablooey, remember we've talked about that before, we could have some serious climate change in many areas for a long period of time, depending on how big it is. So what happens is volcano goes kablooey, the volcanic ash can block out the sun for long periods of time. So these little dust particles, they're called aerosols, they can be propelled into the stratosphere that's way, way up there, and they can stay there for months and even years. Now, think about it. If you had clouds over where you live for months or years, what's going to happen to all the trees? What's going to happen to all the plants? If there are no more trees and there are no more plants, are there going to be animals? Are you going to be able to have clean water or any of those kinds of things? That could be really bad. So these aerosols reflect the insulation back into space. So because we have no sunlight, you're not going to have the trees. The trees or plants are all going to die. Everything around you is going to struggle. You're going to have acid rain on top of it. So could be a bad time. There's less energy that comes to the Earth's surface, cooler temperatures. This happened in 1816. They had a year without a summer, blocked out the sun for a couple months. Not fun. Also happened in the 1990s with Mount Pinatubo, the cooler temperatures. Human causes. Unfortunately, we humans have done a lot of bad things. They're good for us, but not for everything else. Desertification. This is when the trees have been cut down, the grasses have been cleared away, and things turn to like a desert-like area. This is causing for higher temperatures to rise. There's no plants that absorb the heat energy. There's no water in deserts, so that's not going to even things out a bit. The land heats up faster, so that means it's going to re-radiate more heat into the atmosphere. Okay, deforestation also causes desertification. Cut down all the trees, the climate becomes hotter and drier. The heat on Earth's surface, instead of it's being absorbed by the trees, which is what I just said, is going to be re-released. Also, there's less transpiration. Remember, transpiration is when plants release water vapor into the atmosphere. Transpiration is water vapor coming from plants put back into the atmosphere. So what happens is when you cut down all the trees, you don't have as much water vapor going into the air. You have less rain. You have less rain. Things dry out. Bad stuff happens. Okay. Greenhouse gases cause global warming. Carbon dioxide, what happens is those, when you burn fossil fuels, it puts carbon dioxide into the air. What happens is that infrared rays come up, they can't get out. Carbon dioxide stops it from getting out. So then it comes back down and it's going to keep the heat here instead of letting it go back into the atmosphere and above and back into space. Urbanization also does that. Building of cities, you put more carbon dioxide out into the atmosphere because you have more people there, you have more buildings, you have lots and lots of factories, things like that. This is going to result in hotter temperatures, more smog, which is like fog but created from pollution. You have less wind, you have more humid, which kind of contradicts itself that you think that urbanization is going to cause things to be drier, but you actually can create this humidity that keeps the heat here. It can be cloudier, more fog, and you also have more acid precipitation. You have factories, pumps all the pollution into the air, the pollution then condenses, it falls down as acid rain, can be bad for all. Okay, so thank you. That was radiative balance. Use your reference tables.